welcome to the course on biological data analysis and visualization with R. In the last few classes, we have been talking about linear models and how to apply linear models for building predictive models. Okay. So, we have also done some hands-on and we have looked into the problem of multicollinearity. We have talked about two ways of addressing multicollinearity. One is ridge regression and the other is lasso regression. We have seen how ridge regression can help in building better predictive models by identifying the key features from the full data set. In this class, we will be talking about lasso regression. So, we will start with lasso regression and then we will continue with our discussion on stepwise regression. Now, when you do ridge regression or lasso regression, we identify a set of features and we include all those features for building the model. What stepwise regression can do is, from those feature list, it can still identify the best combination of features. Okay. This is something that is also very helpful for focusing on only certain features that gives us the best results. Okay. So, this is something what we will be discussing in this class along with hands-on, and just to remind you about lasso regression, what we will get is a reduced set of independent variables, and weights of some of these independent variables will be estimated to be 0. So, we can discard those variables from the model, right, because they are not influencing the response variable. Stepwise regression, what it will do is it will perform a stepwise addition or subtraction of independent variables to the final model, right. So, this is something again will evaluate, right, the contribution of the combination of the variables in the model, and this is something that is very useful to identify the key set of features, right, which is the best combination of features after you have done the lasso regression or ridge regression and get the best combination. So, this is what we are going to see in this class. We will start with the lasso regression hands-on first and then we will go into the stepwise regression in the hands-on. Okay, so, let us now move on to our console and let us do these steps and then identify these key features and see how we can improve the predictive model. So, here we have the R console, right, and we are working with the same data set as before, right. We have this input data. Okay. This is the data set that we have seen already. So, what we are going to do is, in this lasso regression part, is first we will actually try to do something called imputation. Okay. So, what is imputation is something where we have missing data, right, NA values, we will try to guess. So, imputation is something like a guessing what would be the what could be a possible value for that data. Okay. So, for this NA value we will replace with certain guesses, okay, and this is what we call as imputation. There are many different ways of imputation. So, without going into a lot of details, right. So, we can use this package random forest, right, so, or RF package random forest, right, using random forest method to actually impute the data. And this is something will not run because this will take a long time. Okay. This imputation actually takes quite a bit of time on even on this not a very big data set. So, we will not do this in this class, right. I am sharing the code because I have run this code already to actually impute some of these missing data points. Okay. So, the libraries that we have are the library mice and library random forest. Okay. So, these libraries you can install and then load here. Then what we are doing is we are setting set seed 1, 2, 3, 4. So, if what it will ensure is that when we do this imputation or initialize run these commands, we will get the same output at all times. Okay. Otherwise, it might change when you run this imputation method. Okay. So, the commands I will just very briefly mention, okay, is, and then I will show you the imputed data, okay, without running this. Is the first is mice mod, right. We are using this mice package and we are taking input data and we are taking these columns except the DMYPD. We do not want to impute the response variable, even if we have missing data in the response variable, we do not want to impute the response variable or the dependent variable, right. So, that should be out of this imputation process. The method is random forest and the package that we will use is random forest based on random forest, right. So, here is the method is RF random forest, RF package is random forest, right. So, that is why we are loading this library random forest. Okay, so, once we have this, right, mice model, so we create this new data and we complete this mice model. So, we generate the completed data, that is, so we have the imputed data, but we also need to add the dependent variable value, right. So, the dependent variable value is the DMOIPD, that is the DMOIPD variable column from the input data itself, and we store this as data tab as data frame, right, and use the command cbind, right. We have seen this cbind command already. So, cbind is DMOIPD new data. So, it will column bind, right, put them side by side. Okay. Once this is done, we just use the RM. So, we are removing these parameters, right, from the environment, our environment, right, these are gone, and we write the data tab in the imputed, is a file, right, which we call as imputed filtered merge data list. Okay. So, this is imputed data where we have done something called missing value imputation. Okay. As I said, I will not run this will take a lot of time, and I have run this already before, and I have generated this imputed data, which I will show you after we load this data set. Okay. And we will use this data set for doing the lasso regression. So, you might ask, like, why do we need to do this imputation, because some of the commands that we will use they might throw up error if we do not do the imputation. With NA values they will throw up error. Okay. So, I will just show you this right after we load the data. Okay. So, this is the data tab imputed filtered merge data, and let us see. Okay. As you can see, there is no NA value now, right, we have imputed the data. Okay. So, you might ask, okay, of course, whether the imputations are all perfect, no, definitely no, but at least we will not get any error when we run this model. Okay. Compare this with our original input data, and you will see, okay, we might not be able to see here, we can actually see the NA values and see if we have we can use this command. Okay, and you can see how many NA values are there, right, for each of these columns. Okay. So, that is the column sum. Let us see whether the imputation has worked well, right, and as you can see, there is 0 now. Okay. There is no NA value or missing value here. Okay. So, this part, earlier part is for the input data, right. Before the imputation we had a lot of these NA values or missing values. After imputation you see there is none, right. So, it is 0. Okay. So, that is the missing value imputation that we have done. Okay. So, we will be working with this data tab, right, that is the imputed data, and here what we are doing is simply looking into how many features we have, right, in the data set, and we are first doing something called an lambda value estimation. Okay. This is something that actually will give us the coefficients, lasso coefficients for each of these features. As I said, right, is lasso regression will try to set this coefficient or the weight value to 0 for some of the features. Okay. So, for doing that we first have to build this model matrix, right. So, this is the x value, right, and this is the x. Okay. And then, okay, let us look at the head of x. Okay. So, we have these values x, and except the dependent variable, right. So, we do not have the dependent variable here, we only have the independent variables, and for y we select only DMOIPD, right, and taking this value as numeric. Okay. Okay. And we are taking this as numeric values. Okay. This is our dependent variable. What we are doing next is we want to determine this best lambda, right, from this x y, right. So, again this is something related to the how this lasso regression works. Okay, so we have to determine this best lambda to use in our case, and this will do something called a grid search over these values. Okay, so we are defining this grid from 10 to the power, right, from 10 to the power 10 and then minus 2, right. So reduce this, right, by minus 2, and then we create this range of values over which we will search, the model will search for the best lambda. Okay, so that's how we define this. We define the x, y, and we define the grid value. Here now, for doing this, we have to do something called cross validation in GLM net package. So cv dot GLM net package x, y values. Okay, and okay, so it will take a bit of time, right. In the meantime, what we can do is, okay, we can now look into this cv dot out. Okay, what we get. So minimum lambda minimum, index measure, etc. Again, without going into a lot of details of how this mathematically how this works, we take the best lambda, which is the lambda minimum. Okay, and this, let's look into best lambda is 0.1199 or this 0.1200. Okay, so that's our base lambda value. Okay, now we create this again this GLM net package, right, using x, y, and lambda equals to grid. We have the out value. Okay, and head out. Okay, so again we see a lot of these parameters like lambda, grid, etc. Without going into, I will not go into again all the mathematics behind this, and we then identify the Lasso coefficient from this predict out type coefficients s equals to base lambda. Okay, and what we will get is the Lasso coefficients for this. Okay, so we learn this GLM net package, right, over this grid, and then for the base lambda we take out the coefficient values, right. We can predict these coefficient values, and then 1 to length, right, that is the names of the data type, right, how many features do we have here. Okay. All right, so what you see now, so this is where the whole thing will start, right, because we have not discussed the mathematics of this. This is not really related to this class, but we have now got these Lasso coefficients, and this is where we need to understand what is happening. Okay. So as you can see, for Lasso coefficients, so what you have is this intercept, right. Then you have these coefficients. For some features, these coefficient values are 0. As you can see here, for example, this feature here, the coefficient value is 0. Okay, so you will see a lot of these features, the coefficient values are 0. Okay, so you will see these features, and then you have these features where coefficient is non-zero. Our goal is to identify those features where this coefficient is non-zero, right. These are the features that have some influence on the dependent variable. Okay, and that's what we are going to do is we will identify these important variables from this Lasso coefficient set, and by saying this Lasso coefficient not equal to 0. Okay, so again I am running this command. So out of this Lasso coefficient that we got, choose only those where Lasso coefficient is non-zero. Okay, and this will give us a list of features, right. Again we have a list of features that have non-zero coefficient value. What we will get is the names, right, in variable these names, right. We need to get the names of these variables so that we can create a new data set, right, with only these features and run the linear model again. Okay, so that's the idea. Like ridge regression, what you see here, we now have about 56 features that have non-zero coefficient values. In ridge it was around 36, in Lasso it is about 56. Okay. All right, so let us count the number of, so what is the length of these features, right, how many important features we have is 56 or 57, it is kind of identifying. Okay. All right, so that's what we have, right. So what we will do is using these commands as before, right, we use these commands in ridge regression as well, is we will create a Lasso input data taking only those features that are in this important variable list. Okay. So input data only take those column names which match with the important variant list, right. So, only those 56, 57 whatever we have, we want to use those features for our predictive model. Okay, so this is the dimension now, we have 56. Okay. All right. So, from this now, for this we also need to add the dependent variable or the response variable, which is the DMYPD, right. Again we will use the cbind command and add this DMYPD column, right. We have seen this before, and we also will rename this just to keep parity with what we have done. We will rename this input data DMYPD to DMYPD, okay. And then we can see the final outcome, and we see this, okay. So, here the first column is the dependent variable DMYPD, and we have some of the features that we have identified by Lasso regression. Once this we have created this Lasso input data, the steps are exactly same as before. We will create this training index, we will create training data, test data set from this Lasso input data, and then we will run the linear model. We will look into the explained variance on the training data and the predicted R square. Okay. So, this is what we are going to do. These commands are exactly same as before. We are taking 80% of the training data, right, and 80% of the total data in the training data, and then rest of them will be test data, right. So, we have used this command as before, right. Here we are working with Lasso input data, and we are taking 80% of the full data as the training data, right. So, you are creating this training index now is by sampling. We have training data now we have created, and rest of them will be test data. Okay, so, this is done. So, let us run this linear model, okay, and this we are now familiar with this, right. This is we are using this lm command DMYPD, then we are using all independent variables that we have in this Lasso training data, and we are running this on training data, okay, and we get the summary of this. The only thing that we need is this explained variance, okay. We can see this summary, of course, okay, and the adjusted R square is 0.44, okay. But you might argue that there are more features here, right. Lasso identified more features compared to reach. So, maybe that explains the adjusted R square. So, we need to look into the predicted R square as well and see how well this method performs, okay. So, what we will do is we will just store this in EXPV, right. This is around 0.44. So, this model explains about 44% of the variation in the data. We now want to do this, build this prediction, right, and using this command predict on the test data and using this lm mod Lasso. The actual values are this Lasso test data DMYPD, right. These are the actual y values and these are the predicted y values, and again we can look into this actual predicted to see how well this model is doing, right. Okay, this looks okay. There is some correlation, right. It's not just random points all over the place. So, we have some correlation, it seems. We can test that by correlation test, and yes, there is correlation, right, 0.65, and there is significant p value is less than 10 to the minus 16, 2.2 into 10 to the minus 16. So, there is significant correlation here. Okay, so, let us now go into the actual calculation, formal calculation, right. As before, we define this full data frame, right, and get the actual predicted where there is no NA value, and then we calculate this predicted R square, right, and see what is the predicted R square. Okay, so, we have 0.42 predicted R square. So, that is a significant improvement even over reach regression. Okay. So, if you remember, right, originally when we started with and we built the model with all features that we had, our the adjusted R square on the training data was very high, right, 0.56 or 0.57, but our predicted R square was disappointing. When we did the reach regression, we got some improvement, right. Our the R square, adjusted R square on the training data was improved, like it reduced a little bit, 0.25, 0.28, etc. And our predicted R square improves substantially, right, to 0.1 to 0.2, etc. We got that. here in lasso regression we see we have improved upon both the training R square, right, on the training data as well as the predicted R square, which is 0.42. Okay, so that's a good improvement over the earlier models. Okay, so this is something, again, as I said, if we run this one more time, you will see the results might be different. So I'll just run this and see whether this results that we got actually is stable. Okay, so it's not as high as 0.42, but it's still better than what you have seen before. It's around 0.31, and the explained variance is 0.44, right. So these are significant improvements over even over ridge regression. So which means lasso regression is actually identifying the important features here. And as before, we can look into the important variant list. And here we have this list. Again, they will have some biological meaning, which we will know in your data set. I know some of this importance of some of these features, right. So that actually is very reassuring. We see these features here. Okay, so next we can do the stepwise regression. As I said, we can we do even better? Can we look into the sets of features or combination of features that gives us the best prediction? Okay. So we will do something called stepwise regression, and we will use this package called OLSRR. Okay. So this is a package, our package that allows us to do this OLSRR, the stepwise regression, and we will use this function OLS step both AIC. Okay. So you might ask, what is this AIC? So this is a specific criteria that we will use to actually choose the combination of features, but you can also use different sets of different criteria built in this package. You can look into the manual and you can see whether that will change the performance of the stepwise regression. Okay, so I have this model installed here, library OLSRR. We can also see the R package OLSRR if we can access the manual, right. So this package is loaded now, and what we will first do is we will run this the linear model, and then we will run the stepwise regression to identify the best set of features. Okay. So OLSRR package. Okay, here it is, and okay. Okay, so you can see what we will do is we will use this OLS step backward, we will step both adjusted R square AIC. You can use different criteria here, right. OLS step backward, right, only backward, right, or forward, right. We will use both, so both forward, backward, right, addition, subtraction, so that we can get to the best set of features. Again, in both you have also this adjusted R square, AIC, p value, R square, SBC, SBIC. So these are all explained, right, what these criteria mean. Again, we will not go into all of this, right, what actually this SBIC and so on. Okay. So these are features, these are the criteria for choosing the best combination. Okay. So what this model will do, it will add feature and it will calculate this specific criteria, and out of this, so multiple steps, it will choose the best outcome, right, based on this value, AIC value or BIC value. Okay. Alright, so the step is first is to build this linear model, right, and we are going, I am going to demonstrate this with the lasso input data. You can run this on ridge input data or any input data, right, starting from the first input data that where we did not do any variable selection using ridge regression or lasso regression, but remember that is going to take longer because you have a large number of features and calculating all possible combinations might take a lot of time. So it's actually ideal if we apply this on ridge data or lasso data, because we have reduced the number of features already. So that's why I will demonstrate this on lasso input data. So first I'll run this linear model, right, using the LM function, and the next step is to actually do this OLS step both AIC. This is a function from this OLSRR package on this model itself. Okay. So let's see what we get. It might take a bit of time. And once we run this, we will then look into this mod AIC, we will then get the most important variables from this process, and then we will again build this new input data, right, from step process and stepwise regression, and then we will see whether we see any improvement in the performance of the model. So, here is a big summary of this model summary, right, as you can see, and this will give you a stepwise summary. So, the base model, you have certain values of AIC, SBC, SBIC, R square, adjusted R square, as well as you should have p value, right, anyway. Okay, so, we are using this criteria. So, these are different values, we are using this criteria, right. We want to minimize this AIC value and choose the best model based on this AIC criteria. Okay, and here it is a summary, right, it is showing us like what are the features that have been added and how this information changes the AIC value or SBC value. Okay. So, our focus is on AIC. So, here you see like how these models have been added and then what is the final outcome. Okay. So, what here is the model summary, we have final model output, we have R square, adjusted R square, we have predicted R square 0.417. Okay. So, that is good. Again, what is AIC is mentioned here, again we will not go into this information criteria. Based on this, we have got these results. Okay. And then finally, we have the parameter estimates, right, the beta values, and then standard error, right, standard deviation, etc., and the significance of these parameters, right. So, here you see the significance here. Okay. And this is something list of parameters that are likely to be important. We can extract all of this information, right. We have looked into this, we can actually extract this information and okay. So, what are the important features that have been identified here? Okay. And we can identify these variable names, right, using this command step variable list minus the model coefficients 1, right, and let us look into this variable list. Here the number is much less, right, it is 24 only, 24 features we have. Okay. So, if you look into the lasso regression or ridge regression compared to that, step variation actually have chosen even fewer parameters from the lasso data, right. So, we are working with the lasso data here and we have run the stepwise regression on the lasso data. From that, we have chosen even a smaller number of parameters that are likely to be the most interesting ones and might give us the best model. Now, once we know these variables, what we will do is we will create this new step input data, and this is something that we are familiar with now, and from that we will also need to add this dependent variable as before, DMYPD we have added, and we need to rename this column, right, to just DMYPD instead of input data DMYPD. Okay. So, let us look into the step data, and you can see, right, we have the first column is the dependent variable DMYPD, and then we have the 24 independent features or independent variables. We have built this now, so we can go into the training and test process and again evaluate the performance of the model. So, here it is, right, we are choosing this training index or sampling this training index, again taking only 80% of the data from the full data, and then rest will be our test data. Okay. So, once we define this index or sample this index, we can define the training data and the test data. Okay. Once this is done, we simply run this model now on the step training data with only these features, and let us look into the summary of this model, right. Okay. And adjusted R square is 0.437. Okay, that's good, right. And this is also stored in here is 0.437 and 0.44. Let us look into the prediction, right. That is the most critical part for us, and we can again look into the whether these actual values and predicted values are correlated. Okay, that seems to be a pretty nice correlation, right. Can we look into the correlation coefficient? we can also evaluate this correlation, right, by correlation coefficient, and yeah, so correlation is, there is significant correlation 0.69 and the p value is here, this is significant. There is another way to look into this correlation is by drawing a line, right, where y equals to x, right. These values should be equal, right, in the actual world, but in reality, in theoretical they should be same, but in reality they are not. So, we can evaluate, right, how closely related they are by drawing a line y equals to x, and that is what I am going to do through this plot by saying AB line a equals to 0, it should go through 0, and then b equals to 1 because this is a y equals to x line, line width 2, line type is dotted, right. So, 2 and color should be blue, and see how it looks like. Okay, so, this is not bad, right, these values are actually around this line. So, there is good correlation as we have seen as well, right, correlation test. Okay, so, the final thing we need to do is we need to calculate this r square on the predicted value, right. This is something what we are going to do. Okay, and r square is 0.45. Okay, so that's pretty good, right, from where we started without any feature selection. Okay, with lasso regression and doing stepwise regression on the lasso input data, we have now reached a point where we can actually get very good predicted r square value, right. At the same time, we are explaining the variance in the training data. So, what you have seen now is we can improve these models, right, and build very good predictive models using by removing this multicollinearity or addressing this multicollinearity issue, right, which we can also reduce the overfitting. Of course, there is scope for improvement, as you can see, right, r square is 0.45. So, we can say, okay, why not r square 0.8, 0.9, but if you compare, right, where we started with, this is a significant and substantial improvement, right. So, again this is something we will have to run multiple times to actually evaluate this carefully, right, because there could be variation in the explained variance depending on the composition of the training data and the composition of the test data. So, you can see this is varying, but again that is why it is important to run this maybe 100 times or 1000 times to evaluate the actual performance, get the mean value of that explained variance and predicted r square and the standard deviation values. Okay, so, let us that completes our hands on lasso regression and stepwise regression. Let us go back to the presentation and I will just summarize, right. So, what we have seen, lasso regression identifies features with non-zero weights or coefficients, right, and we took those features and built our model for prediction, and we then added the stepwise linear regression model on the lasso data, and then it can identify the best set of independent variables out of those 55 or 56 independent variables that lasso identified. Out of those, stepwise linear regression identified 24, 25 variables that could give us very good performance in terms of or much improved performance in terms of predictive power as well as explaining the variation in the training data. With that, we will conclude the linear regression part. We will talk about the non-linear regression in the next class. Thank you.